Most creek walkers unknowingly step over a visual cue that seasoned gem hunters instantly recognize. A dark red glint peeking out from black sand or gravel. The mistake lies in assuming all red stones are just colored quartz or common river-worn pebbles. But under the right light and angle, that faint flash could be the surface of a pyrope garnet, almandine, or even a spinel, minerals with commercial potential if properly identified and extracted. Red gemstones like garnet and spinel tend to resist erosion better than host rock, concentrating in placers along creek beds. Yet without understanding the subtle difference between their luster and shape versus ordinary creek gravel, most people never see them for what they are. In uncut form, garnets are often dull and rounded, but still carry a characteristic vitreous sheen, like glass held underwater, compared to the matte, earthy finish of jasper or red shale. This alone narrows the field of possible candidates dramatically. The real advantage comes from recognizing where to look. Red gem indicators rarely sit exposed on dry banks. Instead, they cluster in microtraps, crevices in bedrock, inside coarse riffles behind boulders, or nestled within dense black sand patches after storm washouts. These are places where the natural hydrodynamics of water flows slow enough for heavier minerals to drop out. Since red garnets can reach a specific gravity above 4.0, well above common rock, they naturally settle into these depositional catchments. In early autumn or late spring, when creeks run low and visibility improves, trained eyes can sweep a small section and immediately spot the color contrast. But many red stones look convincing only until dry. That's why it's critical not to dismiss a find too quickly. Some true garnets dull out once removed from water, only to revive under loop or when moistened again. The tragedy is that creek hunters often discard promising stones based solely on poor lighting or a superficial assumption. Those who learn the value of delayed judgment, and who take the time to test, not guess, are the ones who leave with the real prizes. But even those first glimpses are just the beginning. What separates promising color from true gem content lies in the next layer of clues: texture, luster, and shape under close inspection. It's easy to be fooled by color in creek rocks. Deep red draws attention, but the real separator, the test that quickly weeds out low-value lookalikes, is luster combined with shape. A true red gemstone reveals itself not through hue alone, but through how it interacts with light and how its geometry holds under erosion. Begin with luster. In gemological terms, this is the quality of light reflection from a mineral surface. Most valuable red gems, garnets, spinels, rubies, exhibit a vitreous to subadamantine luster, meaning they reflect light like glass or slightly more intensely, especially when wet. In contrast, red jasper, a common false positive, shows a waxy or dull surface when dried and lacks that quick flash under natural light. Take a moment. Wet the stone, rotate it gently, and note whether light scatters diffusely or bounces back in distinct highlights. It's subtle, but repeatable. Shape is just as diagnostic. Most garnets, particularly almandine or pyrope varieties common in metamorphic terrains, naturally form dodecahedral or trapezohedral habits. Even in heavily eroded creek environments, these original crystal forms leave behind traces, edges, faces, or pointed terminations that rounded pebbles don't show. A garnet might be partially smoothed by water, but still reveal faint ridges or flattened faces that hint at its crystalline ancestry. Compare this to typical creek cobbles. Red sandstone, iron-stained quartz, or shale fragments often break irregularly and polish into amorphous blobs. They have no internal symmetry, no recognizable pattern. Even red glass, another frequent imitator, lacks the consistent geometry that garnet preserves in part. Under a 10 times loop, a real garnet may also show conchoidal fracture and fine internal grain, rather than a grainy, porous, or bubbly matrix. One low-tech but effective trick: scratch the surface lightly with a steel blade. Real garnet will resist it entirely, showing no mark. But softer red imposters like jasper, Mohs 6.57, or ironstone will often yield a fine scratch. Do this on the underside or edge. Never the best face. And note both resistance and any resulting streak color. By combining these two reeds, luster and residual shape, you eliminate most of the debris that frustrates beginners. Instead of hauling home a bucket of red rocks just in case, you're now working with a smaller, more promising batch. These are the stones worth testing further, worth isolating from the pan or sluice, and worth running through higher effort processes. But one challenge remains. A few red lookalikes are still convincing under visual inspection, even with good luster and form. To catch these, you'll need to understand where these minerals tend to gather, and why certain creek spots produce more genuine gems than others. Where exactly in the creek does the real concentration of red gems occur? And what signs on land point the way? Topic 3 maps the flow logic behind natural gem traps. The most valuable red gems don't sit randomly in creek beds. They follow the physics of water movement and the geologic memory of the land. Understanding where to look isn't guesswork. It's a matter of reading terrain, spotting flow interruptions, and knowing how density drives deposition. Start with the basics. Red gemstones like garnet and spinel are significantly denser than most surrounding materials. Garnets, for instance, range from 3.5 to over 4.3 specific gravity, while average creek rocks hover around 2.6. This difference plays out in how they travel through water. In high-energy environments, lighter particles keep moving downstream, but heavy minerals settle out first, often abruptly when the current slows. Knowing this, experienced hunters target 3 specific creek features: inside bends, plunge pools, and bedrock exposures. Inside bends are deposition zones. As water moves through a curve, its velocity drops along the inner edge while increasing on the outer edge. The result: heavies like garnet, magnetite, or even gold spiral inward and sink. These bends often reveal a natural riffle system, sand and gravel organized in subtle stripes or layers. If black sand appears in these zones, check closely for red glints embedded within. Plunge pools form where water cascades over rock steps or falls, scouring a basin beneath. As the downward force strikes bottom, it creates a temporary vortex that sorts materials by density. Red gems frequently get trapped at the deepest point, particularly where the pool bottom is lined with hardpan or unfractured stone. After storms, these basins reload, making them prime targets for repeat checks. Bedrock is the ultimate trap. In shallow sections where the stream has worn down to exposed metamorphic or igneous base rock, look for crevices, cracks, and scalloped pockets. These microtraps hold concentrates that haven't moved in decades. Use a crevicing tool, or even a stiff brush to sweep out compacted sediments. Heavy red stones lodged here, especially those resisting even strong water flow, are far more likely to be authentic garnets or spinels than what you'll find scattered in open gravel. Not all creeks qualify. Red gem-bearing terrains are tied to specific upstream geology, regions with historical metamorphic activity, particularly those rich in schist, gneiss, or skarn, produce garnets through regional metamorphism. Skarn zones, where magma intruded limestone, are especially rich in diverse garnet types, from grossular to andradite, sometimes with gem-grade clarity. If your creek drains from such a zone, every test you do gains context. Also note the role of slope and gradient. Steep creeks produce turbulent flow, which cleans the channel, but moves heavy material quickly unless blocked. Gentle sloping creeks may seem less dramatic, but they allow for better settling and often develop long-term gravel bars where red gems accumulate incrementally over seasons. These depositional clues aren't static. Seasonal flow changes can rearrange a creek's entire layout. A productive inside bend in spring may become buried under fresh gravel by fall. That's why careful record keeping, photos, coordinates, sampling notes is crucial. You're not just hunting stones. You're reading a living system, mapping its patterns over time. Still, even a perfect spot produces a mixed concentrate. Among the red fragments, some are magnetic, some aren't. Yet a surprising number of fakes pass the initial visual and terrain filters. How do you unmask them efficiently in the field? The answer lies in a simple, portable tool that exposes imposters hiding in plain sight. Topic 4: brings in magnetics to cut through the clutter. A red stone nestled in the black sand may pass the luster test and come from ideal terrain, but still be worthless. One reason? A class of deceptively attractive red imposters that behave more like iron or than gemstone. That's why the next move, after visual sorting and terrain selection, is to bring out a magnet. It's one of the cheapest, fastest diagnostic tools a field hunter can carry, and for red stones, it's surprisingly revealing. Many creek concentrates contain iron-rich minerals that mimic the deep reds and surface shine of garnet or spinel, but lack any gem value. Hematite and magnetite in particular can develop reddish oxidation films, or even appear blood red when polished by water. At a glance, they might seem promising, but their magnetic properties betray them instantly. Use a neodymium magnet if possible. Even a small one can create a clean divide. Hold it over your cleaned pan concentrate or directly over damp red stones. Genuine garnet and spinel are not magnetic. They won't respond. No twitch, no pull. But if the red candidate jerks toward the magnet, even slightly, it's likely magnetite or a hematite-magnetite blend. These materials often appear in the same heavy sand zones as garnets, but can quickly swamp your concentrate if not weeded out. Some hematite forms aren't strongly magnetic, but may still contain enough iron to give a weak attraction. This is where a second trick helps: the sweep test. Place your suspect stones on a plastic tray or flat surface and drag the magnet slowly underneath or across it. Real gems will remain inert. Magnetic imposters will subtly pivot, roll, or inch forward even if they don't leap toward the magnet directly. Red jasper, often confused with garnet due to its color and dull luster, is non-magnetic, but its very opacity makes it easy to dismiss with a loupe. Magnetism is especially critical when you're dealing with fine concentrates. Small garnet grains in the 1 to 3 millimeters range can blend perfectly with iron-rich sand unless you separate them by behavior, not just appearance. Another benefit of the magnet sweep is speed. When you're working a productive creek zone, the volume of black sand and red particles adds up fast. Rather than carry out heavy, mixed bags, the magnet allows you to triage on-site, saving weight, time, and processing effort. The clean batch that passes visual, luster, and magnet tests is already a high-probability sample. Still, not every red stone that avoids the magnet is a gem. Some non-magnetic materials, dyed glass, shale, sandstone, can slide through the same net. To eliminate these, the next step is to challenge them physically. Use hardness to prove or disprove structural integrity. When red stones scratch, or get scratched, the truth often comes out. Topic 5 puts hardness on trial, with nothing more than a file or quartz shard. Red creek stones that pass visual inspection and avoid magnetic response still have one more common pathway to failure: softness. The gem market only values materials that can survive cutting, setting, and wear, and that means high hardness. Most garnets and spinels fall in the 7.0 to 8.5 range on the Mohs scale, while many common red lookalikes barely clear 5.5. The field hardness test, done right, quickly separates these classes with no lab tools required. Start with a reference point. Quartz, rated Mohs 7.0, is both abundant and reliable for testing. A broken shard of quartz river pebble, A quartz crystal, or even a piece of unglazed porcelain tile can serve as your hardness probe. Alternatively, silicon carbide SiC sandpaper, around Mohs 9, is cheap and packs flat in your field kit. You don't need fancy kits or numbered picks. You just need to know which side marks the other. Here's the test. Find an inconspicuous edge on your red stone and firmly drag your quartz point or SiC strip across it. If the stone gets scratched, it fails. Simple. Real garnets resist abrasion from quartz. In fact, almandine garnets are frequently used industrially as abrasives. Proof that their hardness isn't just theoretical. If the test leaves a visible groove, or if powder is generated from the stone itself, you're almost certainly dealing with a soft imposter. Flip the test. Try to scratch the quartz with your candidate. If your stone leaves a trail or mark on the quartz surface, it may exceed 7.0 Mohs. And that's a promising sign. Some pyrope or spinel varieties reach up to 8.0 plus, rivaling topaz or even approaching sapphire hardness. These are the stones that survive handling, transport, and lapidary work, and attract buyers. Watch out for shales, sandstones, and dyed glass. These materials often appear as rich reds with a smooth finish when wet but crumble or mark easily under even light pressure. In dry conditions, they feel softer to the touch and often show layered fractures or an earthy texture. If a steel pocket knife or even a fingernail affects the surface, you can rule out gem potential immediately. Another tell. Sound. When tapped against a metal tool or another hard stone, garnet gives a higher-pitched click or ring, while softer materials respond with a dull thud. It's not foolproof, but over time you'll develop an ear for density and cohesion, especially when evaluating borderline cases in the field. This stage, hardness testing, acts as a gateway. It's the final low-effort field method before moving into active concentrate recovery. Once you've screened for color, luster, magnetism, and hardness, you're left with stones that deserve deeper effort. And that's when the pan comes out. How do these promising red stones behave under a proper pan concentrate? And what subtle traits emerge in black sand that loops miss? Topic 6 dives into the flowing spiral, where red gems truly separate from the crowd. Once a red stone passes the visual, magnetic, and hardness filters, the next confirmation step is deceptively simple. Put it through the pan. This isn't just about pulling out individual gems. It's about reading the character of the entire concentrate. Red gemstones behave distinctly in the pan, and experienced fieldworkers can spot them not by color alone, but by how they settle, resist motion, and reflect light amid the black sand. Begin with classification. If you're not using a sieve set, at least hand sort by size. Coarse from fine. A number 20 sieve, 0.85 mm, and a number 40, 0.425 mm. Bracket the grain sizes where gem fragments concentrate most efficiently. Garnet, with its high specific gravity and weather-resistant nature, often turns up in the -20/+40 fraction. Small enough to move through riffles, heavy enough to remain behind in the final pan layers. The black sand line is your signal zone. As you swirl off the lighter overburden, keep an eye on what remains at the back curve of the battue or pan. In rich zones, you'll often see a narrow line of garnet grains forming just ahead of magnetite or hematite. Look for translucent red fragments, not opaque maroon. These translucent grains catch and hold light as they roll. Their edges may be smooth, but their internal structure will still flash under shifting water. Some even display mild internal zoning, which under loop inspection can hint at gem quality. Unlike gold or magnetite, garnet doesn't flash in a metallic sense. Instead, it glows subtly when caught at the right angle. A single red crystal with a glassy face may reveal its geometry as it refuses to move under the swirl. Heavier than quartz, but less stubborn than iron. One of the most telling signs comes in the friction test. Once you've swirled your pan down to concentrates, flick a fingertip across the heavy line. Garnets roll with resistance. They don't skate like sand or cling like magnetite. Their tactile response is somewhere between grit and ball bearing. Get used to how this feels, because in the field, especially under cloud cover or muddy water, touch can be more reliable than sight. Keep a vial or snuffer bottle handy to isolate promising red grains. If unsure, pan them again. Garnets will always resettle predictably in the same band, no matter how many times they're agitated. This repeatability is a crucial confidence builder and can help you map hot zones with a high degree of trust. But pan behavior isn't everything. Some red materials that mimic garnet will survive the swirl and even look right, but lack the density or structure to back it up. That's why the next confirmation step, once you've collected a few candidates, is specific gravity. At some point in the process, color, luster, and resistance to scratching aren't enough. To truly verify whether your red stone is a garnet or just an inert pretty pebble, you need to measure how heavy it is for its size. Specific gravity, SG, is the go-to metric, and in the field, it can be estimated surprisingly well using just a container of water, a scale with gram precision, and a little patience. The principle is straightforward. Weigh the stone dry, then weigh it submerged in water. The difference between those two weights gives you the volume displaced, and the ratio gives you the specific gravity. SG equals dry weight submerged weight. This method has been used for centuries and requires no more than a jeweler's scale and a plastic cup of water suspended on the same scale platform. Let's walk through a real example. Suppose you find a deep red stone weighing 6.50 grams dry. You suspend it using a fine thread or a small cradle that doesn't touch the sides or bottom of the container, and its weight underwater reads 4.15 grams. The difference, 2.35 grams, is the volume displaced. So, 6.50/6.50 to 4.15 equals SG of approximately 3.70. That result lands comfortably within the range of almandine garnet, which usually falls between 3.5 and 4.3, depending on iron and magnesium content. By contrast, red jasper or quartz, common fakes, will usually test between 2.6 and 2.7 SG. They'll appear almost light in hand when compared side by side. It's especially noticeable in small stones. A genuine garnet will feel dense, compact, and unexpectedly heavy. Over time, you'll develop a tactile intuition that aligns with the math. If you're doing this test in the field, secure your scale on a level surface and shield it from wind. Use a paper clip or thin wire to suspend the stone, and subtract any added weight from your setup if needed. Repeat your measurement for accuracy. Consistent results within plus or minus 0.02 SG points are enough for confident field identification. Some synthetic materials, especially high-index red glass, may mimic the weight of garnet, but not the behavior under other tests. That's why SG should always be paired with luster, shape, and hardness. Together, they create a diagnostic suite strong enough to justify professional verification if the stone shows commercial promise. There's one more benefit to SG testing. It confirms multiple red types. Garnets vary widely by subtype: pyrope, almandine, spessartine, all with slightly different SG ranges. Spinel, while similar in hardness and appearance, averages slightly lower SG, around 3.58, helping you distinguish between them when multiple red minerals appear in the same creek system. But not every high SG red stone is valuable. Some low-quality garnets and dense red minerals may meet all physical tests and still fall short under magnification. That's why the next layer of separation involves exposing common false positives. Stones that feel right but crumble under optical inspection or provenance scrutiny. Few mistakes cost more in creek gem hunting than hauling out a sack of red stones that turn out to be worthless jasper. The heartbreak isn't just emotional. It's wasted labor and lost opportunities. Jasper is everywhere, especially in stream environments fed by volcanic or sedimentary terrain. It's red, it's tough-looking, and in water, it can glow deceptively. But even skilled collectors have misjudged it for pyrope garnet, especially when worn smooth. Fortunately, 3 field-level traits and 1 critical loop test break the illusion. First, transparency. Even heavily included garnets show some degree of translucency when held to sunlight or a bright flashlight edge. Tilt the stone and look through the thinnest edge. If no light passes through and it remains fully opaque, it's likely jasper. Jasper's dense microcrystalline structure blocks light entirely, while even low-grade pyrope reveals internal depth, color zoning, or a dull glow. This alone can screen out half the false positives in a well-washed pan. Second, internal grain under loop. At 10 times magnification, jasper reveals a grainy or fibrous texture. You may see flecks of iron oxide or faint layering, remnants of its sedimentary origin. Pyrope, by contrast, tends to break with conchoidal fracture and lacks visible granularity. Its surface under loop appears glassy and uniform, sometimes with resinous glints or curved break lines. One visual cue. If your red stone's surface looks frosted or slightly dusty under loop, it's likely not a garnet. Third, color consistency. Pyrope garnets range from dark blood red to purplish tones and often display subtle internal zoning. Jasper tends to hold a flat, brick red to ochre tone without variation. This uniformity, combined with opacity and grain, is a strong disqualifier, even if the stone passed a basic hardness test. Still, jasper can mislead in one more way. It's tough. Many forms resist steel or quartz scratches and may even mimic garnet's Mohs 7 rating. This makes hardness alone insufficient. That's where weight steps in again. A well-formed pyrope garnet will often weigh 15 to 25% more than a jasper of equal size. Carry 2 confirmed samples for side-by-side comparison. Real garnet feels denser in hand, often surprisingly so. There's also a color trick underwater. True pyrope gains depth. Its red turns richer or takes on a subtle wine hue. Jasper may brighten but stays flat, even under full immersion. This light behavior reveals structural differences invisible when dry. But the biggest giveaway comes from thermal and electrical conductivity, especially when dealing with borderline cases. If you're unsure, if the stone feels right, looks right, but won't quite give up its secret, then it's time to test how it handles heat and current. That's the next layer of truth. Even after visual, hardness, and weight checks, a few red stones still linger in the gray zone. Convincing to the eye, tactile in hand, yet questionable in origin. That's when conductivity testing becomes your most decisive ally. Red garnets and spinels have well-documented thermal behaviors, and some synthetics or treated stones fail spectacularly under this scrutiny. These aren't lab-bound procedures. With a pocket thermal tester and a basic electrical probe, you can close the case on-site. Thermal conductivity testers, commonly used for diamond verification, measure how quickly heat disperses through a material. While garnet and spinel are poor thermal conductors compared to diamond, they still display consistent, traceable resistance profiles. Most genuine garnets, especially pyrope and almandine, show moderate conductivity, registering slowly on testers or not at all, depending on calibration. What's important isn't the number, it's the behavior. Test a suspect red stone by placing the thermal probe on its clean, flat surface. Real garnets tend to absorb heat sluggishly but evenly. Treated glass, by contrast, often gives erratic readings or causes the tester to spike and fail calibration. Some synthetics show a sharp temperature drop followed by an abnormal rebound. signals of inconsistent internal structure or filler materials. If you test twice and get two wildly different results, be suspicious. Electrical conductivity adds a second layer. Most garnets are insulators. They don't carry a current. Spinel, too, is electrically neutral in most cases. But some synthetic or imitation materials, especially those doped with metallic oxides or constructed as composites, will show measurable conductivity. Using a simple conductivity pen or multimeter set to resistance mode, touch both probes to opposite edges of the cleaned stone. No response? Good. A faint signal? Investigate further. A strong response? You're likely holding a fake. Moissanite, a well-known diamond simulant, often trips up testers because of its high thermal conductivity and weak electrical flow. But moissanite is rarely red. Still, if a colored stone gives any conductivity spike, it's a red flag for lab-grown or altered material. Some gemstones can be heat-treated or dyed to simulate garnet color. These stones may look authentic, but their thermal response will often mimic glass or resin composites, materials that hold surface heat rather than diffusing it inward. You can sometimes feel it. Genuine garnets cool quickly after being held. Fakes retain warmth. That simple thermal lag can be felt even without a device if your hands are sensitive and conditions allow. When taken together, no magnetic pull, passes hardness and SG, low thermal conductivity, and zero electrical activity, you're narrowing the sample to natural, unaltered red gems. But there's one more layer of strategy: geological context. Where did this stone likely originate? And does the surrounding terrain support its presence? Every red gem in a creek has a backstory, an upstream journey from its point of formation to your pan. Understanding that origin isn't just academic, it's strategic. Red garnets and spinels don't form randomly. They crystallize under intense pressure and heat, and their presence in creek beds points directly to specific rock types and geological structures. If you can read those signs, you'll not only find more, but potentially locate the mother lode. Start with metamorphic terrains. The most common red garnets, like almandine and pyrope, originate in high-grade metamorphic rocks: gneiss, schist, amphibolite, and mica-rich formations. These rocks result from the slow compression of sedimentary layers deep within the Earth's crust, often during mountain-building events. Over time, the pressure causes aluminum and iron-rich minerals to recrystallize into garnet. When these rocks weather, garnets are released and washed into local streams. If your creek drains from a hillside with visible mica schist or banded gneiss, you're in prime garnet country. Look for weathered outcrops, especially those stained dark brown or reddish from iron oxide leaching. On sunny slopes, these exposures may shimmer faintly due to mica flakes, an indirect indicator of garnet-bearing rock. Nearby, soil may contain angular red grains even before you hit water. But don't ignore skarn zones, geological boundaries where igneous rock intrudes into limestone. These contact zones, often associated with mining districts, produce a wide variety of garnet types, including grossular, andradite, and even gem-grade varieties. Skarns are messy but rewarding, fractured, mineral-rich, and prone to producing not just garnet, but vesuvianite, epidote, and spinel. If your area has a history of skarn-hosted ore bodies, particularly those mined for iron or copper, investigate the drainage systems below them. Spinel, another red gem often mistaken for ruby, also forms in metamorphosed limestone, especially where magnesium is present. In terrains with known marble formations, especially contact metamorphic zones, spinel may occur as isolated crystals or clusters. These crystals resist erosion extremely well and can travel miles from their source, but they tend to concentrate in very specific channels, those with low gradient flow and consistent sediment buildup. In older mining regions, Tailings piles or waste rock from historical operations may contain overlooked garnets. During the early 20th century, many industrial garnet types were discarded due to poor cutting tools. Today, some of those same stones meet lapidary standards. Research old claims and revisit them with modern test logic. Maps help. Geological survey maps often mark metamorphic zones, skarns, and intrusive boundaries. In the US, for example, garnet-rich terrains run through the Appalachian Belt, parts of the Sierra Nevada foothills, and scattered skarn systems in the Rockies. Globally, they're common in orogenic belts, places where continental plates collided and folded the crust. These maps also show known garnet-bearing lithologies, helping you target feeder creeks with greater confidence. The key insight here: gems follow geology. A single garnet in a pan is useful. A cluster, especially in consistent size and luster, demands upstream investigation. Don't just collect, backtrack. Terrain clues can turn casual finds into viable prospects. Most red gem hunters focus on the visible, the flash of color, the glint in the pan, but miss a crucial efficiency multiplier: grain size control. Using sieves, even a basic two-tier mesh system, you can radically boost your identification accuracy, isolate gem-grade fragments, and save time on testing. The trick lies in knowing where garnets tend to settle by size, and how consistent that pattern is across productive terrain. The number 20 mesh, 0.85 millimeters openings, and number 40 mesh, 0.425 millimeters, are the workhorses. Why? Because garnets that survive transport without breaking tend to cluster in this range, small enough to avoid breakage under water pressure, but large enough to still preserve diagnostic traits: luster, translucency, and crystal form. Stones finer than number 40 often lose their identity in magnetite-rich concentrates, while those coarser than number 20 may be too few or too battered to evaluate quickly. Start by dry screening your collected creek material into 3 fractions. Plus 20, larger than 0.85 millimeters, dash 20/plus 40, target zone, and minus 40 fines. The dash 20/plus 40 bracket is your sweet spot. Within this size class, garnet grains often show preserved dodecahedral outlines, clean fracture planes, and under loop, even subtle color zoning. Spinel fragments in this range tend to show a more blocky habit, but still retain sharp terminations or conchoidal fractures, a strong visual cue against river-rounded jasper or glass. When panning or sluicing, this sieved material behaves predictably. Gem fragments in the dash 20/plus 40 group settle into a narrow stripe just ahead of black sand. If you're recovering consistent red grains in this fraction, you're in a live zone. Repeat panning confirms it. If garnets consistently concentrate in this mesh class from multiple spots along the creek, you've mapped a productive drainage vein. Mark it. There's another strategic advantage to mesh sorting: elimination of noise. Coarser gravel often contains distracting quartz or shale chunks that mimic color or weight. Finer material introduces magnetite, silt that hides garnet grains. By working in a controlled grain size window, you reduce testing volume and raise the signal-to-noise ratio. That means faster field calls and more reliable data for mapping deposits. If you have access to water on site, wet sieving is even better. It prevents static cling, separates clay-bound fines, and helps settle materials quickly by weight. Use a nested sieve stack, waterproof tubs with a bottom catch, to process samples in 2 to 3 minutes per site. After sieving, pan just the dash 20/plus 40 batch. Every red stone that survives the magnet, hardness, and SG tests in that fraction deserves closer inspection. And here's where the payoff increases. This method is not just repeatable, it's scalable. Once you lock in a productive size, class, and location, you can grid sample systematically, build a density map, and even prepare to bulk test or trench with minimal wasted effort. In other words, sieving isn't just about sorting. It's about narrowing the window through which the highest value stones emerge. But even with size, shape, and behavior aligning, one final filter remains that's often overlooked: fluorescence, or the lack of it. Some fakes glow brilliantly under UV, while true red gems do something rarer. What does it mean when your red gem stays dark under UV? And why might that be a good thing? Topic 12 explains how ultraviolet light reveals what the eye alone can't. Most gem hunters expect excitement under ultraviolet light. Bright glows, brilliant colors, immediate confirmation. But with red gems, the opposite is often true. The most valuable garnets and spinels don't shine under UV. They stay dead calm. And in this rare case, invisibility is a mark of authenticity. Let's start with expectations. Many synthetic materials, dyed stones, or treated glass exhibit strong fluorescence under long-wave UV light. They may glow pink, orange, or even white-blue in a dark setting, often an artifact of coloring agents or rare earth dopants added during manufacturing. It's impressive to watch, but when a red stone fluoresces unnaturally, it's often a red flag. True pyrope garnet, almandine, and most natural spinel varieties show weak to no response under UV. In gemology labs, this inertness is a known trait. Not a bug, but a feature. To run a field test, use a pocket-sized long-wave UV flashlight in low ambient light. Place your red candidates on a dark cloth or tray and sweep the beams slowly across the surface. A strong glow means you're likely looking at glass, dyed quartz, or a synthetic corundum simulant. A faint, inconsistent flicker might occur in some garnets, especially those with trace chromium. But anything vivid or stable is suspect. Real garnets under UV remain muted. They may show a dull reddish-brown tone or nothing at all. Spinel can sometimes emit a weak chalky red, especially in certain magnesium-rich variants, but it's rarely consistent or bright. The silence under UV helps you screen. If everything else checks out and the stone stays dark under ultraviolet, it strengthens your case. Another trick: shine UV light while your red stones are submerged in water. Some glass composites lose their glow or shift colors in water due to surface treatments breaking down or scattering differently. Garnet's dullness remains consistent dry or wet, another checkmark in its favor. It's also worth noting that some treated rubies or synthetic red sapphires, lab-grown and high-index, will glow intensely due to artificial flux residues. These stones can appear convincing in visual tests, but betray themselves with strong UV reactions, especially around fracture zones or internal bubbles. Here, then, is a reversal. Under UV, true red gemstones don't perform. They withdraw. And that quiet behavior gives you a critical decision-making tool. If you're building a field collection, use this as your late-stage filter. Stones that pass all other tests and stay dark under UV are worth keeping, cataloging, and possibly submitting for lab confirmation. But how do you prove a field spot is more than just a lucky scoop? You need repeatability, something that doesn't rely on luck or anecdote. The next step is structure. Putting your finds on the map, grid by grid. What happens when you turn a few lucky garnets into a mapped, repeatable deposit zone? Topic 13 breaks down how to grid sample and confirm a real source.